recording, making it official. Happy Thursday. Welcome back to school. Only one more week until spring break. Is anybody doing anything fun?
I'm defending my comps.
Defending comps. That's a blast. So what you mean to say is that you're going to be celebrating being a PhD candidate during spring break.
Well, apparently in our area, you're not a candidate until you pass, until you propose.
What?
Dissertation.
Okay.
So,
That's a semantic distinction.
yeah.
The Graduate College recognizes post-comprehensive exam as admission to candidacy. So, PhD candidate on your email signature. Post haste. Yes. Anyone else doing anything fun? Yeah, I've never been anywhere fun for spring break in my entire life. It's always catch-up time. Because it's demoralizing, I feel like, to go and then have all of this waiting for you when you come back. So I prefer to go on vacation late May after I turn in grades, and I'm like, peace out, I'm going to the beach. So hopefully we'll get to do that this year. Do you know what I'm doing on spring break? I'm teaching a workshop. So I'm teaching a workshop for APA on clustered multi-level models, 2 90-minute workshops. I will send out the link if you folks are interested because it's free. They have other workshops that they're going to be happening this spring. One is on missing data by Craig Enders, which I would recommend. He's a very good presenter, very clear communicator. There's also a GIMME, I think you had told me about that acronym. I'm not entirely sure what it is, GIMME, but it's a model of some kind. There's a workshop on that too, so if you want to learn what that is. So, lots of fun things for us to do over spring break. So I put up the webpage here because I made a couple changes. First off, I have not forgotten about your homework ones. I just can't quite get there because I'm trying to make sure I have class material for both of my classes every single time. And because I can never leave well enough alone, I always have to fuss with it, which takes time. But I have not forgotten. It is on my list. Project outlines are the next thing that you should be working on. So if you have, this is meant to be the beginning of the dialogue. So if I want to get a chance to see, just as a sort of general level, what data you're working with, if you don't know what you want to do, that's fine. Just tell me what you're interested in, and I can help you figure out what the model would look like and point you towards resources if there are things that we haven't covered. So let me know if you want to talk about any of that. The other thing that I changed is I bumped stuff after break back a week. So I had homework 3 due on 3/27, and this morning I bumped it another week because we haven't started the material that homework 3 is supposed to be over yet. So you have nothing due when you come back from spring break and nothing due the following week so that you can get your project stuff moving along. My intent is to have feedback to you on your outlines as soon as I can so that you can all start working on that kind of stuff. So that's my plan. Any questions about any of that? Okay. The other thing I did this morning is update. So we're going to start lecture 4 today. I really think it's going to happen this time. I did not think we'd get very far into it though, so I posted example 4A and 4B and their associated files for next week. So that's all new, and that will probably take us longer than a week to go through. But then we'll see how I want to reorganize the rest of it that follows. So that stuff is new. Alrighty. So I will shut that off, try and preserve some bandwidth. And last time, this is about where we were, trying to get the plot back on modeling change in latent variables. So I want to start back in this and re-go over the latent basis aspect because I feel like there's a connection that's missing that once you have it, it will go much better in terms of what is the purpose of this. So this model right here is my last invariance model where I've placed as many constraints as I could without harming fit to make sure that the measurement model is functioning the same way over time. So in these models, the measurement model refers to the factor loadings. So these slopes right here of how much the factor predicts each outcome. It refers to the intercepts, so the expected outcome when a factor score is 0, and the residual variances, which is the amount of variability in each outcome that is left over that is due to not the factor, something else. So that's the layers of constraints that we've placed In addition to those parameters, we are allowing the same outcome to have a residual variance over time. So for instance, block design at time 1 gets to be related to block design at time 2 simply because it's block design, so irrespective of the common factor. So that's the measurement model part. Any questions on that much? Okay, so that, if you had SEM or CFA or anything like that, should sound reasonably familiar. Now the structural model. That terminology refers to factor things. So factor means or intercepts, factor variances or leftover variances, factor covariances, and potentially the use of what's known as higher order factor to predict those things. So at this point, in terms of the structural model, we have estimated the means for the cognition factor at times 2, 3, and 4. The mean is fixed to 0 for identification at time 1. That sets the scale of the model in terms of what the latent variable of cognition is like. Likewise, in the structural model, we've estimated the factor variances at times 2, 3, and 4. The factor variance in this model is constrained to 1, again for identification. So we have basically the scale of this outcome is that it has a mean of 0 and a standard deviation of 1 at the first occasion, and then we'll see if the mean changes over time, if the variance changes over time. And all of the covariances are estimated across the 4 factors. So we have 6 covariances there in the structural model as well. So if I were to think about this latent variable as an observed variable, what we have here is essentially a saturated means unstructured variance model. That's what this is. We have as many means estimated, basically let them be whatever they want. We have let the variances be whatever they want, let the covariances be whatever they want. The output option Tech 4 generates predicted means and variances and covariances and correlations for your latent factors. So one of the things that I did for my own use, but also I think would be helpful for us to see, is just write them down. So inside the download packet for this unit, I have what are the means as estimated by 4C, the residual invariance model. That's my new baseline. So this is what the pattern looks like. On average, cognition is decreasing over time. And based on just looking at these numbers, it looks like it's an accelerating pattern of decrease. More decrease as time goes on. Likewise, for the variances, they appear to be increasing over time, meaning individual differences, people are spreading themselves out. And here are the latent factor correlations. I didn't write down the covariances because those are difficult to interpret given differences in variances, but I've got correlations. So like this is the data that any higher order factors would be responsible for recreating. The means, variances, and covariances of the lower order factors. Okay, with me so far? Okay, so then we are adding higher order factors whose job it is to recreate this pattern of mean change through the mean of the intercept and slope factors. So the fixed intercept and the fixed slope, we're going to spend 2 parameters essentially to estimate this pattern of change on average. Fixed effects are the means of the latent variables. Likewise, the model for the variance. If we have an intercept factor and a slope factor, then that implies a pattern of changing variance over time. So we're trying to recreate this increase in variance with random intercept and random slope variances. So a random intercept would say that the variance is constant over time with constant covariance. Adding a random change slope introduces quadratic heterogeneity of variance over time and non-constant covariance over time as well. If you look at the pattern of correlation, the occasions that are closer together are more related in time. That's a pretty common thing. So this pattern of differing correlations over time, as well as this pattern of differing variances over time, is a giveaway that it's not just a random intercept that I need some sort of random change slope of some kind. What kind it is up to me. I could do linear, I could do quadratic, I opted for a latent basis here, since that's one that you haven't seen yet. Okay. Questions on that much so far? Yes.
So just to be clear, my handout is saying 4B. Model 4B is this. 4C, am I missing a model? Or is this, you're saying this?
4C is the last one we ended up with. Yeah, I think that's just a mislabeling error. This is 4C. I think. Partial residual variance. How many do I have? Let me double check. Thank you for the question. It's always helpful to be on the same page, right? Oh, yep, it is. It should be 4B. 4B is the last one. I didn't make it to C in this handout. Thank you. I will change this to say B, and then I think we're good. Just a labeling issue.
So we should be able to find this in the output of, like in our PDF too, right?
Yes, we should. So here's the model 4B, and in our output, so I'm on page 10 right now of example 3. It fits fine, fits well actually. So we have factor loadings. This is my measurement model. So this is relating the lower order factors. We don't have higher order factors yet, but I'll call them that because that's what they're going to be. Lower order factors to the observed outcomes. Then we get factor covariances. So this would be like the off diagonal of an R matrix that's saturated. Unstructured, excuse me, wrong class. It's saturated in the SEM class, it's unstructured in the longitudinal class, but it means the same idea. All the things, all possible things. Next are residual covariances of the observed outcome that is the same variable over time. Bunch of those. Then we get into factor means. So this is my saturated means for what the factor's mean would be at each occasion, where 0 is the first occasion for identification. Next are the observed variable intercepts, their expected outcome given a factor score of 0. Next are factor variances. So this would be the diagonal of this unstructured R matrix. And then not the factor residual variances of the observed variables. Whatever's left over in block design, for instance, that's not due to cognition. So that's where those numbers came from. Okay. Are we ready to move on to the next one then? Or other things you want to talk about? Yeah, please.
So why is it that block 2, 3, and 4 are held constant, block 1 is not for the residual variance?
Because this was one of the constraints that made the model fit significantly worse.
Okay.
So
So
these
that's
two.
the modification indices from before.
Yep.
Okay.
Yep. So those two wanted to be different. There's more leftover variability at time 1 than at the rest of the occasions. I can live with that. Particularly at time 1, because if it's the first time you've seen a task, then there's additional sources of variability or measurement error that you wouldn't expect after you've become familiar with the task. So, okay, other questions? Yes, sir.
Yes, one related to the factor loading for the first item that we are using in the model 5A.
Yes.
Because we are using that 5.9 because that's related to a factor variance set to 1 in
Yes.
our baseline model.
Yes,
But
comes from right there.
What happened if that factor loading was not held equal and we had some of those factor loadings different? Can we choose any other item related to the factor?
Yes.
Okay.
Yeah, the first one is just because that's typically done, but any item whose loading is invariant over time.
Yeah. Right.
So when the factor loading for block design is 5.972, that translates into a factor variance at the first occasion of 1. Now in this model, I've nailed it down so that the factor variance is 1. In the next model, I'm going to nail down the loading instead, so the factor variance gets to be estimated, but the total variability at the first occasion should still be 1 because I fixed the loading to what it ended up being when I fixed the factor variance to 1. So I'm keeping it on the same scale, but rather than nailing down the factor variance at 1, I'm nailing down the loading that corresponds to a factor variance of 1. The reason that I have to do that is that these lower order factor variances are going to be partitioned into how much is due to random intercept, how much is due to random slope, and how much is due to residual. So the leftover factor variances are going to be the residual variances at level 1 in the R matrix. That means I can't just nail it down at 1. It has to be free to become a different number. But I want to keep the model on the same scale in terms of what the parameter estimates mean. Okay. Still with me? Excellent. So now, 5A, which is your clue that there's going to be at least one more, because I had to make a minor modification to it. So the new part in gray then. So the measurement model is exactly the same for how the outcomes relate to the lower order factors. The only difference is that I have changed the way I'm identifying the model by fixing the loading to what it was in the previous model. That way the total variance at time 1 will be approximately 1 still.
I'm sorry, say that one more time.
Yes. So I have not changed the measurement model, but I have changed the way the latent variable is identified. Rather than fixing its variance to 1, I fixed it to the loading that corresponds to a variance of 1. That way, what like the variable itself means is still mean 0 variance 1 at the first occasion. And that's an arbitrary choice. You could have mean 5 variance 10, like whatever, right? You just need a number to pick so that everything else can solve itself around that. Okay. So let me do this part first. Inside the box here. This is all new code. We are defining the latent intercept and latent change factors. You can think of them as higher order factors in a confirmatory factor analysis context. Intercept is defined by fixing all of the loadings for the lower order factors to 1. So think of it this way. When we write out multi-level equations, there's U0 sitting in the level 2 model for beta 0. Put a 1 in parentheses in front of it in your head, because that's essentially what's happening. When you fix the loadings to 1, you're just adding that number equally to all the occasions. So I have defined it as an intercept. Because I've fixed all the loadings to 1, that means I can estimate its variance. So the rules of identification still apply at this level too. The slope, I have decided to make a latent basis. So the pattern here is nailed down at 0 at the first occasion, nailed down at 1 at the last. You can choose which occasions to put constraints on and what they are, but you need at least 2 constraints for this to be identified. This way of doing it means that the total amount of change is 1. And the loadings are going to tell me what proportion of that total amount occurred by time 2 and by time 3. So it's a nonlinear function where I'm letting the data figure out what exactly kind of nonlinear it wants to be. Latent basis. Yes, sir.
So it's just the proportion, I mean, I know it's not exactly that, but like the proportion of change from 0 to the, whatever, the next path.
Yeah, relative to 0 is no change, and 1 is all the change. By time 2, how far did you get? By time 3, how far did you get? So if this were overkill, and a linear change function were sufficient, then what I would get back at time 2 would be a loading of like 0.33, and at time 3 would be 0.67. Like equidistant change means constant change is linear. To the extent that these loadings deviate from those values, then it's some other flavor of nonlinear. So that's actually a nested model comparison you can do. Is linear sufficient? Would translate into fixing these 2 values instead of letting them be free. So it's a nested model comparison.
Do all the loadings have to sum to 1, other than, well, besides the one that's fixed to 1?
No, you can do
Okay.
whatever you want. So one of the things like I might do instead is if I were comparing this to a linear function of 0, 1, 2, 3, then I would take this one and fix it to 3. Because then it's like on the same scale of how much time has passed in real time. And the extent to which this deviates from 1 and this deviates from 2 would tell me if this is nonlinear. I could do it that way also. As long as it's fixed, you get to decide how it's fixed. If I wanted to make the end the intercept and say time is 0 at the end, could I do that? Sure, I could. If I did it that way, I might go -1 there for all the change in a metric of 1, or -3 for all the change. When you do negatives though, you might want to give it starting values. So like an M+, I would go something like star -2, star -1 to make sure that the factor loadings are going the right way. So you can put numbers next to the stars, and that means the place where the searching algorithm is literally going to start, and see how tall it is at that point. So it can make your models go faster if you give it good starting values, particularly for anything involving variances, loadings, and stuff like that. Okay, but I gotta take these off though, so that when I open this handout in like 3 years, I'm not like, what the hell is this? Because, you know, I'm prone to do that. There we go. Now it's back to how I had it. 0, star, star, 1. Doesn't matter. The numbers are irrelevant. It just needs a scale. Okay, so I've created these 2 new variables, which basically would be beta 0 and beta 1 in terms of our notation system. Next step is to give them means and variances. So inside the brackets, I have to fix the higher order intercept mean to 0 because there's no more information to pass up to it, basically. So the first occasion has a mean of 0. The slope, though, I do need to estimate that because that's going to become the fixed slope. The multiplier that would normally be time in our models. The multiplier of u1, because this variable is functioning like u1. I'm estimating both the intercept and the change factor variances. Those are my random intercept and random slope variances, respectively. And I'm estimating their covariance between them. So this is my G matrix right here. Intercept and slope and their covariance. That's my little 2 by 2G. Where's my R matrix? Level 1 residual variances and covariances. It's not in the box here. It's right here. The lower order factors, variances, are like the residual variances, the part that's not due to the intercept and the slope, the part that's left over that's within persons at level 1. And so I have a constraint that makes them all the same. No covariances are estimated by default, so this is a diagonal R matrix, constant variance at level 1 with no covariance. So this is saying the intercept variance and the slope variance are responsible for all the heterogeneity of variance and all the covariances between these 4 occasions. Okay. Better? A little bit? Can you lie to me at least? Like thumb sideways? Thumb sideways? Okay, because last time it was like, nah. So if we've moved up to sideways, then that's, you know, halfway there, right? That's a latent basis of 0.5, all the way up to thumbs up.
Lisa?
Yes.
I have one question, because based on the code, we are fixing the second order factor intercept mean to 0.
Yes, we are.
And we are also fixing to 0 the factor mean of our lower order factors.
The intercept.
The intercept.
Yes, these are now intercepts, but yes.
Both are constrained to 0.
Yes.
But then we will be estimating the item intercepts?
Yes, we've estimated all the item intercepts, and that's
Okay.
why.
Okay.
Because there's no, like in higher order factor models, where we, like regular, like a higher order factor predicts your 4 lower orders, the factor mean is 0 in both places too, because there's no additional information to be pushed up.
Yeah.
If we had put constraints on the measurement model, then we could have estimated it at the higher level, but then that gets weird because it's the metric of one of the indicators, not the factor per se. So there's an article I assigned in this unit that was published just a year or two ago about this, and basically going through the literature and pointing out all the times people have misinterpreted these models based on the set of identification constraints. So I didn't want to do that. So the metric of the factor is this sort of generic z-score metric as opposed to the block design metric or the pros recall metric or a specific indicator, because all of those are on different scales. Okay. Yes.
Now we are assuming, or we are using the instructor, well, the independent R metrics.
Yes.
The independent instructor with same variance and no covariance.
Yes.
And we have seen before that for some models we can change that matrix and use some alternatives.
Yes.
How could we do that here?
Yes.
And how could we do that? Based on coding too? Should we do that manually?
You can add anything you want to change it from diagonal at level 1 R matrix to something that's not diagonal. So for instance, if I wanted to let the time for variance be free, I can actually do that like this. Even though it's here and it's constrained, it reads the code in order, and that would override it. If I wanted to add, say, a lag 1 covariance, like adjacent occasions get to be related, that would be like T1, T2, T3, P width, pairwise width, which is very handy, T2, T3, T4, like that. If I wanted to make them the same number, it'd be like that. So that would create like a Topolitz lag 1 covariance pattern in the R matrix. You can add anything you want, basically. It doesn't have to be a predetermined pattern. You can just write whatever you'd like it to be. Yep. But I got to get rid of these again so that 3 years from now, I don't look back at my code and be like, what was that? Okay, so here's the picture that goes with the model. I added this line back in. So for those of you who asked me about it, I put it back. The reason it wasn't there is because it's fixed to 0, and so it's like anything that's not in the picture is 0, but to understand what the hell squiggle 22 means, then you need this to be 0, this to be 1, and these are stars because they're going to be estimated by the model. So in the picture, I think this was a linear change function, and I just overwrote it. So text boxes with white fill can fix a number of things very quickly. If you don't want to remake a picture, right, you can always like hack your way into something that looks like it. Okay, so then we have, this is my intercept factor, this is my change slope factor. We have the 4 lower order factors. Their leftover variance is going to be level 1 residual variance. We're saying that that's equal over time, and there's no covariance because the only reason these factors were correlated is because of individual differences in starting point and in change. That's what we're saying. So relative to my previous model, which was essentially saturated means and an unstructured R matrix, is what is this going to fit like? It can only be worse or not worse because we have constrained things. This is going to be fewer parameters than all possible saturated means and unstructured variances. So the objective of the game is to test, based on letting everything be what it wants for these lower order factors, is this structure adequately able to recreate those means, variances, and covariances of the lower order factor? Okay, are we ready to see if it worked? All right. So relative to the previous model, we have lost 6 degrees of, or actually gained 6 degrees of freedom, lost 6 parameters. Let me say it that way. Here's how. I went from 3 estimated factor means to 1 mean of the change slope. I went from 3 factor variances and 6 covariances to 2 loadings for the latent basis factor, 1 intercept variance, 1 slope factor variance, and 1 covariance. So we spent 6 fewer degrees of freedom to recreate the means, variances, and covariances. So this is another point at which I might diverge from someone else in my opinion. For instance, in the textbooks, they were like, look, it fits. Yay me. But no, the actual way to test whether your higher order factor model is adequate is to compare it to the previous best fitting structural model, saturated. And when I do that, it does fit worse, even though it still fits well in an absolute sense. So let's look at the results before we try to figure out why it didn't fit as well. So this part is new. These are my new higher order factor loadings. The intercept factor loadings are fixed to 1. The slope factor loadings, these are the 2 that got estimated. They were estimated at 0.27 and 0.63. So 27% of the change has happened by time 2, but 63% has happened. So it's consistent with this idea of more change later on. But based on just these loadings, we have no idea if this change function is going up or down. This is like amount of the change. To figure that part out, we have to know what the mean is of the slope factor, which is the fixed slope. And it's negative. So the interpretation of this is consistent with the idea of all of the study being a 1-unit change in time. Like the last occasion is 1. So a unit goes from time 0 to time equal 1. And based on setting up the factor loading of 0, star, star, 1, a unit is the whole study. A 1 unit, based on the way I've defined it, is all of the change that could happen across my 4 occasions. So basically, they've decreased on average by about a half a standard deviation in standard deviation units of the first occasion. Oh, no, the plot is the thickening again. You can see it. So this is a total amount because of the 0-1 constraints on the latent base. That's where I'm going. If I had done it as like 0.3, then this would be per year instead, because a 1-unit change is consistent with moving from one occasion to the next occasion. But these are imaginary variables. You can make it whatever scale you want, right? It's pretend, it's cognition. So if this model is adequate, this slope mean essentially combined with the 2 loadings should be enough to recreate the pattern of mean change over time. To the spreadsheet, Tech 4 output gave me the predicted means over time, which are this. I have red here for the discrepancy. Make that one red too, just a second. Okay, so it's nailed time 1, off a little bit on time 2, off a little bit more on time 3, and up a little bit on time 4. So it's not recreating the means exactly, but it's pretty damn close. So if I have 4C is the blue line, and my current model is the orange line, and you can't see the blue one because the model I'm about to show you next is on top of it. But basically my model is orange, and compared to the gray line here, we're off the most at time 3, but that's pretty good. So this looks like a bendy, quadratic-y kind of thing to me. So it worked. Okay, is that much okay? Now I have a lot of power relative to what I'm used to having because I have like 600 cases, which for me is a lot. I know for some of you it's not a lot. And the modification indices figured out that it wants to release time 4 for the intercept. Now that sounds kind of crazy, but think of it this way. Do you remember what we did to test absolute fit of the fixed effects relative to the saturated means and using REML. We had to put in dummy coded occasions to fill in all the remaining degrees of freedom. That's kind of what this would be. It's like I'm off this much. If I just release this extra piece, I can sort of plug the hole in the trajectory. And why it's 4 as opposed to 3, it just, because that's the 4, the loading for time 4 is already fixed to 1. So what this is telling me is that of the total decrement in my fit of about 13, 10 of it could be solved by adding this one thing. So that's what the model is going to be next. The rest of this model, though, with respect to the model for the variance, because we've only talked about the fixed effects capturing the means at this point. The model for the variance has the random intercept and random slope variances right here. Now, everyone in SEM world would be like, look, they're significant because this Wald test tells me that they're significant. People do that all the time. Still the most rightest way to test whether a slope variance is significant is a likelihood ratio test. But this is far enough away from 0 that I'm going to assume it would be significant anyway. But you will see people use these Wald test results for variances without batting an eye in SEM world. The reason that that's not cool is because a Wald test for a variance is the null hypothesis is 0, which is the boundary of what it can be. So the sampling distribution of a variance is not going to be normal the closer it gets to 0, which is then when the Wald test would be the less and less accurate, the closer it is against that boundary. So the further away you move, the less it matters. Covariance between the intercept and slope in this case is not significant, but it's here. This would be the G covariance, G matrix covariance. And then last but not least, what it's labeling is the residual variances. This is your R matrix. So this is my diagonal R matrix structure. 0.044 is the amount of variance at level 1 after partitioning out the intercept and slope variance and putting it over in G. So do you remember what it's called when we put G and R back together again? What letter is that? That's V. What letter is that now? It's sigma. Yeah, you're close though. Yeah, psi is the error matrix, phi or phi is G matrix, V is the sigma marginal put back together again. So I asked for that in the Tech4 output so that I could get the model predicted variances and compare them to what it was in the answer key model. And the discrepancies are here. So it's not perfect, but it's reasonably close to the point where it's happy with it. Likewise, I have the predicted correlations from my model, and I have the discrepancy here, and most of these are pretty close as well. There's only one that's above 0.05 in correlation metric. So it's doing a pretty good job of recreating the means, variances, and covariances on the whole. But to show you what it would look like if we took that advice and fixed it, pink for the new color, because the change is right here. I released the intercept at time 4 to sort of plug the hole in the trajectory where it mismatches. So I spent 1 more degree of freedom, everything else is the same, and now it's not worse than the saturated model with respect to the lower order factors, and everything fits extremely well, perfectly in fact. I have 1 new parameter relative to the previous one, which was right here. There it is. So that's a deviation from the trajectory that's allowed at time 4. Putting that in then generates predictions that are almost spot on relative to what they are up here. And that's why you can't even see the blue line, because the gray line is perfectly overlapping. Likewise, model for the variance over here, now you can see the blue line. That's the answer key. The gray line is our current model after we've added the 1 parameter, and the orange line was the previous model. So still pretty darn close. And I think that's it. And then some words for you. Here is a table that I've made with all the fit statistics that you would typically be reporting in this process. And likelihood ratio tests are also in, so this is the spreadsheet I've been looking at. I put the table in here. So for those of you who are going to be doing these kinds of things for your project, this is the type of table you would make. Rescaled likelihood ratio tests are right here. The difference is you have to incorporate the scaling factor into the -2 log likelihood difference. So you can do that using R. Stata doesn't have a robust ML, so I don't think that's a thing. But you can use my spreadsheet in any package, including with M+. And these are your test statistics out here. The scale difference in -2 log likelihood. And so you just enter these three things under the category of fill in. And then the rest of this is auto-calculated for you. For your own sanity, if you're going to use my spreadsheet, please change the words to match whatever you're doing so that you don't look back at this and go, what? Or if you show it to me in office hours, I'd be like, what? Okay, we made it. So that's how we do change in latent factors. Step 1, make sure it's the same latent factor over time. Step 2, figure out what kind of change model it needs, with the usual processes of nested model comparisons and/or weld tests for fixed effects. If you don't get past step 1, if your invariance falls apart to the point where you're no longer comfortable calling it the same factor, then this is not going to be helpful. You don't have a factor that's the same over time. It doesn't make sense to look at change. Then what you would do instead is something called a factor of curves, which is conceptually the opposite. I would fit a growth model for block design, another growth model for prose recall, another growth model for digit symbol. I'd have 3 growth models. Then I could see to what extent a common factor intercept explains the relationships among my 3 intercepts, and a common factor slope explains the relationships among my 3 slopes. So you're reversing what's lower and what's higher, essentially, in those 2 models. I'm gonna fit this data to that model eventually and post it on the website, so you'll have an example of that. I also assigned an article that has M+ code you can download. So, all right, questions? Zoomers, you hanging in there too? There's some thumbs. All right. Yeah, it's abstract. I'll give you that, but this is how it would work. Anything else that I can help clarify or tell you about before we change gears? Okay, Carl and then Vladimir.
So our model 4B, our answer, something similar to our answer key model, we had our 4 latent variables that were time specific,
Mm-hmm.
and those were allowed to covary at whatever they had to reproduce the data, right?
Yes.
And then in our next model, model 5A, we basically set all those covariances amongst those latent factors to 0.
Yes.
Said that their relationship was due to a higher order factor.
2 of them.
2 of them.
Mm-hmm.
And then I'm like sort of lost on what the big change was in 5B other than like freeing the inner.
I just plugged in one little hole in the trajectory to make it fit better, basically by freeing that intercept. It's the analog to putting in a dummy code for a time-specific occasion in the way that we did to test fit.
I'm just trying to think. So like when you talked about like how do you know what's your intercept and what's your slope? Then like I made them that way, right? I
Yes.
set the intercept to 1, 1, 1, 1, 1.
Yep.
And so the idea of like freeing, I don't know, it's like confusing to me.
Freeing the time for intercept.
Yeah.
Yeah, it's the more intercepts you have to free, the less you can trust that the slope is responsible for change, because those are like exceptions to the process at that point. And for the sake of interpretability, given that the previous model did fit pretty well, it would be a reasonable thing just to stop there, I think. but I wanted to show you what the process would look like of troubleshooting in case it doesn't work out as well for you. But yes, your summary is 100%. Okay, do you have a question too?
Yeah, because in this case we are using a continuous variable for time, but what happens if we want to use a piecewise slope? In that case, we should divide, well, instead of one latent factor, we should use two,
Yes.
and we should include all the factor loadings and all the constraints that we did here for the second factor.
We would need more occasions if you wanted to do a latent basis piecewise, but you could in theory do that. The bottom line is that the shape of your change function is entirely up to you. So you can create a piecewise coding system that would be like, 1, 2, 3, and then it shuts off at 3, and that's your first slope, and then the second slope picks up where that one left off, and it's like 1, 2, 3, 4, 5 for that one. That would be 2 linear slopes. You could have, if you have enough data, you can do any sort of pattern that you want to. But yeah, we are saying what this slope means because of the way that we've set up the loading system. Yep, and with 4 occasions, I could have 2 pieces, but one of them would fit perfectly, like in terms of it'd just be one difference, like 0 versus 1, and then 1, like 1, 2, 3, something like that. Okay, another
So
question?
you would do that with this single higher order, like,
No, I would have a third one then.
you have a third one.
It'd be a third one. So picture the level 1 equation. It'd be beta 0, beta 1 times the first slope, beta 2 times the second slope. That means there's 3 circles, higher order circles at that point. Yep. The circles are the betas. Their mean is the fixed effects. Their variance is the random effect variance. Okay, good. I'm feeling better about this. Maybe you're not, but I am. No, you will not have a homework on this. But you can pick this as a project topic. That would be fine.
Lisa, really quick, the arrow that points from the intercept triangle to eta 2, or squiggle, whatever.
Squiggle 2, 2, yeah.
So that's saying, what is that saying?
That means that the slope factor has its mean estimated so that it can become the average amount of change over time.
Okay, and it's not pointing to the intercept variant, or the eta 1, because the mean for that is fixed at 0.
That is correct. So
Okay.
I could add another line here and another 0 if that would make you feel better.
There's the arrows. Oh, there it is. There's the arrow.
Hang
I
on.
did, that's handy.
Hang on. Let me get it connected. Let go. There. I fixed it.
If we, for whatever ungodly reason, changed the 1 to a 2, would that multiply every